13A we're looking at dynamics and the idea of forces being applied in different directions. So in 13A the first thing we're looking at is something called the resultant force, and we're looking at IJ notation. Now the idea here is that for everything in this exercise you need to consider the vertical and the horizontal components of what's going on. So in these diagrams you've got some arrows pointing in different directions, up, down, left, right, and sometimes in the same direction, sometimes in opposite. We need to look at what's happening in each direction. So I always set these up by looking at horizontal and vertical forces. Now the measure of force that we're using is what's called the Newton, and it's represented by the N here. So we've got a 3 Newton force going up and a 7 Newton force going down, 6 newtons to the right, 6 newtons to the left. So if we look at the horizontal direction, I define positive and negative sort of in a standard way, positive to the right and positive up. So in the horizontal direction we have a force of 6 newtons to the right and a force of 6 newtons to the left. So can you see here I've got horizontal is plus 6, so that's this force, minus 6, which is this force, newtons, the N, in the I direction, so that's the horizontal. Now you can tell of course that that's going to be 0 because these two cancel out. In the vertical direction, which is J, we've got 3 newtons up, so plus 3, minus 7 because it's going down. 3 minus 7, and it's J because this is the up and down, J newtons. We probably should have the N there. So when we look at this, you can see that everything cancels out except for the J components, so a negative 4J newtons. And that's what we call our resultant force. So overall, in this diagram, all that's happening is we actually are pulling the object down. So that's part I. The second part of this question says, what's the magnitude and the direction of the resultant force? And to measure the angle from anti-clockwise from the I direction. So you can see we've got a vector. It's basically just negative 4J. And you know that on a sketch that would be a dot just down here. So the angle measured from I would be all the way around, so it's 270 degrees, and the magnitude is the square root of negative 4 squared, which is just 4. So it's 4 Newton force straight down. For part F, it's the same idea. Horizontal forces, you can see we have plus 5 newtons, and this arrow is pointing in the right this way as well, so it's another plus 5 newtons in the I direction. So horizontally we have overall 10 newtons, and here we've got 15 up, 15 down, so plus 15 minus 15J. So together they make up the vector, and of course the J disappears, it's just 10I. And we know from drawing this that 10I would be sitting right here. It's only pulling across in the horizontal direction. So to measure the angle for this, it's going to be 0 degrees. And the magnitude of this force, because our resultant force is just the 10I that we had here, 10I newtons, the magnitude is the square root of 10 squared. Now when you have slightly more interesting situations like this one here, this one is all about identifying the direction because you're going to have I and J components. So again, 8 minus 5 in the horizontal will give you 3 newtons to the right. Overall is more going to the right. And 8 up and another 2 pointing up as well, that's 10 up, so we're going to have 10J. So you can see our resultant vector, it's a vector with a tilde because it's a vector quantity, it has a direction and a magnitude, is 3I plus 10J, and newtons really, should be an N there. So we've got the resultant vector. The next part of the question was what's the magnitude of the resultant vector? The magnitude is the magnitude of this vector, square root of 9 plus 100, so square root of 109 newtons. Just use the calculator for an approximation. Now for the direction for this one, because we have 3I plus 10J, that really looks like this, just sort of roughly. So there's 3, not really to scale, but it's that kind of, that kind of thing. And it's asking you for an angle. Now you know really what you're dealing with here is a right angle triangle where you've got 10 and 3 like that. So in order for us to find the angle theta down here, we're basically looking at tan of theta equals the opposite over the adjacent, which in this case is 10 over 3, which means that theta is inverse tan of 10 over 3. And you can see in the notes, here, that we've got inverse tan of 10 over 3 is 73.3 degrees. And it's already measured off the eye, so that's all fine. Okay, the next question, question 3, says find the magnitude of F, the resultant force of the 16 Newton and 12 Newton forces in the diagram. Now this diagram here really is an example of the cosine rule, and the reason for that is that if you consider what's going on in this diagram, you've got two sides that you know and one angle that you know, what's called the included. So you basically have this side that you know is 16 newtons, that side is 12 newtons, we don't know this side, but we do know this angle. So in terms of labeling, you can see I've labeled them A, B, C with the A. I'll just go back to what that looks like, because we can use the cos rule here. And it always uses whatever the angle is that you've been given. The side opposite it is what we'd call A. So this is the angle big A and this is the side little a. So yeah, you just basically throw everything into the cos rule. The thing to identify is when you have two known sides and an angle, that's the cos rule. And then putting everything in, you'll actually get your force, F squared, because A is what we have here in the diagram as F, the force. And once we have that, you've just got to take the square root. So you get your force as 25.43 newtons in this diagram. So that's using the cos rule. This situation here is a nice little one, and it's actually really important for us to understand what's going on in the picture. It says a tractor is pulling a barge along a canal with a force of 400 newtons. The barge is moving parallel, so it means going along the river like this. Find the component of F in the direction of motion. So if we have a look at, I'm just going to get rid of this stuff here, what's going on here, you've actually got basically a triangle that you're interested in. It's asking you what's the component of motion parallel to the riverbank, which is that part. Now, blowing that up, that's essentially a triangle with an unknown angle, with a force, which is F here, that's the F here, this part. This is what we're interested in, and we don't know this. But the nice thing is we actually know what the force is. We know that the force is 400 newtons, and we know that the angle is 15 degrees. So knowing those two things, we can actually find this thing. And it's just trig. I'm going to show you this over here on this triangle. This is something you really need to know for this course. So in this triangle here, you know that for y, let's look at this one, we've got opposite. So sine of theta equals the opposite over the hypotenuse, which in this case is y, over the hypotenuse, which we call F. F is generally the resultant force that you have on the hypotenuse. Now rearranging this, we've got sine theta equals y over F, which implies that y equals F, just move the F up, sine theta. So that actually helps us, because if we have a situation where we know the hypotenuse and we don't know a side, we can actually just easily say, you know what, this side is just the length, because it's opposite the angle, it's sine of the angle. And you can probably figure out what the other one is going to be, what the x is going to be. Here it's the adjacent. Cos of theta is adjacent over hypotenuse, which in this case is the adjacent x over the hypotenuse f. That means that cos of theta equals x over f, and then moving the f up, you can see that we end up with a similar equation, which in this case tells us that we've got this x that we didn't know being able to be given by f cos theta. So that helps us out, because if we know one side, if we know the hypotenuse, and the angle, we can very easily state the opposite and the adjacent sides. So now in this question, if we return to this, we know that this is 15 degrees. We know the hypotenuse is f. We're interested in the adjacent side. So what that means is using this rule, this is our adjacent, this is our opposite side. We know that this is going to be f, which is 400, cos theta. So 400 cos 15 degrees, because theta is 15 degrees. And you can see then, going back into the notes, we've just used the calculator and found that's approximately 386. And this is newtons because it's a force. That's the force that's in the direction of motion. You'll also notice that in this question there is another force which we aren't interested in because it's actually a detrimental force for pulling the barge along. But there's a force here which is perpendicular to the riverbank, and that's what actually makes it so that not all of your force is pulling the barge along. And of course, to find that, if you were interested in finding that, that would be F sine theta. It would be 400 sine 15, if you wanted that, but we're not asked for that in the question. So it's really, really good knowing this. Definitely put this in your notes so you know. All right, the next question is question 12. This one says find the component of the force given in the direction of the other vector. Now this question is actually a really good one just for me to quickly draw out for you, because as soon as you see the word in the direction, you have to remember vector resolutes. So this, or resolving a vector into parts. So this has got in the direction of, that means make that your vector here, 2i minus j. We want the component of the force of another vector, which means there's some other vector going on here, 7i plus 3j, that's in the direction of. So we're essentially looking for, I'm just going to make this a little bit shorter. We're essentially looking for this part here. If you can see, that's like the shadow, the projection down of this vector. We're actually interested in this red vector here. And remember that this is the vector resolute parallel in the direction of the other vector. So the formula for that is here. So we've got, this is basically your A, this is your B. It's in the direction of B, so it's A dot B on B dot B times B. That's B, that's A, and you just use your vectors. So it's you can see here that the force is a vector, and the force here, it's not a magnitude like it was in some of the earlier things here. This was asking for a magnitude. This is actually a vector, so you leave it with the I and the J. Question 7 is looking at resultant force of these particular diagrams. Now I am going to do probably these ones just so you can see what's going on. So in these two questions you're interested in the same idea, splitting up into horizontal and vertical components. Now it's actually a bit hidden here, but there is a little 3 Newton force here, and then the other one, the blue one, is a 4 Newton force. Now a good idea with this is to always split this up into parts. Okay, so instead of dealing with the 4 Newton force as it is here, it's better for you to split this up into parts, the horizontal component and the vertical component. Okay, so you know that the horizontal component would be 4, because it's a 4 Newton force, cos, because it's adjacent, 40 degrees, that would be this one, and this would be 4 sine 40 degrees. So now I'll get rid of this. Instead of thinking about this now, we don't really care about this anymore. We really only have these two and this one, because these two blue ones represent that blue one. So now when we look at the components, we can go horizontal. And you can see in this question we're being asked, in the following, find the resultant force in IJ notation and then find the magnitude and the direction. So we're looking at horizontally, you've got 4 cos 40 degrees plus 3, because that's the blue one plus the red one. And then vertically, the force you've got is 4 sine 40, and it's newtons. You've got two things. So now when we return to the solutions here, you can see that I've just used the calculator and just found out what they are. Make sure your calculator is set in degrees. So the horizontal part and the vertical part, and a vector is always going to be expressed as I and J. So the horizontal overall component with I is the coefficient of I, the vertical component is the coefficient of J. So our magnitude, this is our vector here. This is our resultant force vector. You can see that it's bigger in the I direction because more of the force is going along the horizontal than going vertically. The next part was find the magnitude. Magnitude, remember, is just to take a vector. If you have a vector, remember that if you have a vector which is AI plus BJ, the magnitude of the vector is just the square root of A squared plus B squared. So that's all that's going on here, just squaring the coefficients. The direction, always for these direction ones, you know, when you're dealing with something like this, if you know what the vector is, which we do here, we've got I and j components. Just roughly drawing this, you can see that when we put that together, it looks a bit like this. There's 6 and there's 2, there's 3. So 2.57 is kind of there. It's a little bit sort of there. So this is the vector r. If we're interested in the angle theta, again it's the idea of tan of theta equals the opposite, which is the height, over the adjacent, which is the length. And so that means then that tan is inverse theta of that fraction, which is that one there. So that's why we end up with, with 22.98 when you put that in the calculator. If you want to convert to DMS with the CAS, remember you can use the little magazine and you can do DMS, degrees, minutes, seconds. This particular one doesn't say, so you could have just left it as a decimal. Same idea with this one. Again, I'm just going to show you splitting this up so you can see the components here. We've got some horizontal and some vertical components. I'm going to do these in different colors. Here we've got the 7N force. It has 2 parts to it, a horizontal and a vertical. The horizontal is 7 cos 20 degrees. The opposite is 7 sine 20. It's 7 because the 7 is the hypotenuse. Once you've got those two, you no longer need this one. This is now represented by these two, as is the one back here. So instead of having this, we can see that the horizontal, this is a 6 Newton force here. This will be 6 cos 30. This one will be 6 sine 30. And that means we no longer need this because it's represented by these two. So then when you break this up, you can see horizontal is, if that's, generally make this the positive direction, 7 cos 20 degrees minus the other one. And the vertical, both of these are going up, you'll notice. So both of these are actually going to be positive. You don't have one going, the other way. And if you plug those into your calculator, you're going to find that you get these numbers here. Remember that the horizontal component is the I coefficient and then the j is the vertical. You got your resultant vector, we call it r. Magnitude is just the magnitude of a vector, and the direction again is inverse tan. It's always inverse tan the j over the I, j over I, so you can get your direction. The next one is breaking up 2 forces acting on a particle. Find the sum of the resolved parts of the force in the direction E to F, and find the sum of the forces in the direction of the 8N force. So we're going to do, first of all, the first part of this. So I can just sort of show you just on the diagram here. The 8N force can be divided into this part, which is 8 cos 40, and the 15 degree one down here, the horizontal component of that is 12 cos 15. So you can see them both there. They're in the I direction. The up and down components of this part would be 8, because that's the hypotenuse, 8 sine 40 degrees. This would be 12 sine 15 degrees, but it's negative because it's going down. This would be going up. So that's why we've got the subtraction. So an I and a j, and then putting them in the calculator. Remember degrees, everything's degrees in this section. You get this vector. It says find the sum of the resolved parts of the forces. So when it says in the direction of E to F, can you see E to F is the horizontal? So it's basically saying what are the forces in the horizontal only. So realistically, we really didn't need to do this whole thing here. We could have just actually gone I forces and just added these together, 17.72 newtons in this direction. For part B, this is where it's a little bit tricky, and I'm actually going to draw this one. So part B says find the sum of the resolved parts of the forces in the direction of the 8 Newton force. You can see that's the 8 Newton force up this way. Now, if you're trying to find a sum of forces in a direction, can you see in the first part of the question, you're asked to find them in the E to F direction, and that's horizontal. It's always better if you're looking for things in a direction to make that horizontal, okay? So imagine taking this image and rotating it slightly so it looks like this. The 8n is flat, then you've got a little part there where you've got the 15 degrees and the 40 degrees, and this is 12 newtons. So all I've done is literally just, and this dotted line is the E to F. There's E, there's F. So it's just this vector is this thing here. So you can see that the angle between these two is the total. So it would be 55 degrees. Now what you're looking at is basically a diagram where you're looking at, for the question, what is the component of this vector that's on an angle that's going in the 8n direction. So you're basically saying, for this vector here, I'm going to make it purple, what is the bit that goes there that's going to add onto the 8n? And we know from the work we've done, this part will be the force here, 12. It's adjacent because it's right here, cos the angle, which is 55 degrees. So we actually have in this direction, in the 8n direction for this question, we have two things. We have this, and remember the 8n force is going in that direction as well. So let's look back at the question. Find the sum of the resolved parts in the direction of the 8n force. So you can see now, this is where this came from, because we're looking at this part plus the 8n. There's two things, two vectors going on, this black one and this purple one. They're the two forces in the 8n direction. So resolved in that direction, adding them together, you get 14.88 newtons. So direction is really important. Whatever you want things to be resolved in, make that direction horizontal. All right, we're nearly there. I think there's two more. So this one, we've got, I'm actually going to do 17 first while I'm here because it's a very quick one. Find the magnitude of the resultant of two forces of 7n and 10n, so 7 newtons and 10 newtons, acting at an angle of 50 degrees. Now what you'll notice is the diagram I've drawn has made one of these things horizontal. So that means you don't have to be resolving into horizontal and vertical components for one, because it's already horizontal, right? So for this diagram, we know that the 7n part here has a horizontal part down here, which is 7 cos 50. And it has a vertical part here, which is 7 sine 50. So over here we've got horizontal, 7 cos 50, 7 sine 50. And for the 10 Newton force, there's only the horizontal because we made it the horizontal. You can choose what direction this is in. Always put one along the I-axis to make your life easier. So in the horizontal, we've got 10 newtons plus the bit of this one here that's horizontal, so the 7 cos 50. You just add those two, add those together. There's the I component, there's the J coefficient. There's your resultant and your magnitude. So very similar to the other ones we've done. This one to finish off, I will do this whole one because it is a little bit awkward, the wording. So we've got 3 forces, 5 newtons, 7 newtons, and P that are acting on a particle at O. Find the value of P that will produce a resultant force along O to X if the line of action of P newtons is perpendicular to O to X. So there's a lot going on. And you can see that they've actually given you a diagram because it's just a lot happening. So let's have a look. We've got our things. Find the value of P. So we're interested in, what this is. That will produce a resultant force along O to X. All right. Now what that means is we only want this object to be going this way. We don't want to have any up and down motion. So what we should do is we should figure out, first of all, don't worry about P for now. Let's figure out what's going on in these directions here. Okay, then we can sort of figure out what we need to counterbalance them. So I'm going to just color code them. This blue one, this is a 7, so this is opposite. So that means this is 7 sine 35 degrees. This red one is opposite and it has a 5 Newton force as the hypotenuse, so this is 5 sine 35 degrees. So overall our vertical forces, I'd define this as being positive and this as being negative. So vertical forces, we've got 5 sine 35, take away 7 sine 35, and this is degrees. Now I'm just going to cheat and have a look what that is. So I can see here that, and I've actually done this slightly differently, but that's okay, that these two things are not going to give us 0 because they're not the same. All right, so we're going to look at what else we've got going on here too. This P, you'll notice, is going up, which means it's positive. So we've got all of that. That's all of our vertical stuff. Now, in order for there to only be motion in the OX direction, only motion in O to X, we have to have no vertical net force. So what that means is that all of this stuff that we've just written down, all of this force, has to be equal to 0. So that effectively means that P equals, and you can rearrange this, you end up doing this, just taking all this stuff to the other side, like that. And you're basically just finding the difference and making sure that you, account for it. So in the notes you can see here, we've just rearranged a little bit. And in doing that, you'll find that this part here is 1.147. So P has to be 1.147 newtons to balance this out, to make sure we have no vertical movement, just movement in the horizontal direction. You'll also notice that I didn't bother resolving this into the two parts here. I didn't bother thinking about this part or this part because the question is interested really only in making the vertical motion 0. So we don't really care about this. But there are two other components here if we think about the horizontal. So that's basically it for 13A. It's all about identifying horizontal and vertical components and also making sure that you're familiar with using triangles and particularly this idea of the F sine theta and F cos theta. And also remembering that the units we use for this section, the force units are N for newtons, and that we do generally measure direction of motion off the I-axis. So in all those cases where we did that, it was a matter of using inverse tan because you're looking at the opposite over adjacent to find the angle theta.